born either in January or February. Okay. So how are we going to do this? So raise your hand if you were born in January or February. Okay, so I'm going to assign Gonzalo. Yes. So you are just the representative. So all of you just... Is Ricardo. Maybe Ricardo will be for another one. Okay, so all of you in this group, just coordinate with Ricardo, with Gonzalo. Okay, so raise your hand if you were in March or April. Okay, so let me see. So are you going to be around, Natalia, or not? Okay, so coordinate with Natalia. Yes, yes, you are assigned. Let's see, May and June. Okay, so you will be. So just, I mean, the thing is like, just, go to you, just discuss who wants to be kind of the representative. So, I just need basically one person to install the code. So on Friday, we can really try to write papers, just to illustrate. If you don't want to do it, it's perfectly fine. If you don't want to do it. Okay, so let's see. This was May and June, I believe. So July and August. Oh, this is a small group. Okay, so I think you will be the representative. Well, just the person, and then you discuss who want to be assigned. Let's see, September and October. Okay, so I will have to choose Rogerio. And I guess November and December. Okay, so so maybe, yes, I'm sorry, yes. Okay, so it's clear. So, what it will be very nice is for tomorrow, if you really can come to me, just one person, just the representative. So what we're going to do on Friday is, this representative per group, we're going to just basically try to write a paper. So we just need basically like one person with a laptop and just basically seeing if everything goes well. Really, that's everything. I was born in August, but I will, I will be here. Yes. So, okay, any question regarding this? I think, yeah, please. So right now, it's like we need to install a software. This software might need a little bit of massage. So, if we try to install this on Friday, it might fail, and maybe we will not be able to, let's say, write a paper. So it will be just, let's say for the first group, it will be nice to have a person, who is maybe sitting there and everybody in that group just looking, let's say, at that computer, so you can really exactly see, how the paper is being written. And as I told you, I cannot do this for everybody because, we have to, at the end of the day, pay for this model, so it's going to cost a significant amount of money. But if we do for 6 groups, it's perfectly fine. So we just need to install the software. Sure, if everything goes well, it's 5 minutes. PIP install Denario, but let's check. And then basically I have to give you my keys because we need this to run it. And that's it. So it should be really like, hopefully 10 minutes, but just to make sure that on Friday it works.
So when do we meet?
So it would be nice if for tomorrow you tell me who is the person that we should install this thing, and that's it. I think you have a question, yes, please. Which days? Which day? Should I say or no? August 7th. So, okay, any other question? Please. Yes. In Linux might not work, so let's not even try. You have Linux, then you cannot be, or you can install a virtual machine, no, but it's maybe better not. I mean, it might work, but we don't know. It's better if it's a Mac or a Linux.
Yeah, no, I have a Linux.
You have a Linux, yeah, then. I thought you said a Windows. Okay, sorry. Then yeah. Sorry, Mac or Linux? Yeah. Still jet lag. Okay. Any other question? Okay. So I think what we should do is try to finish the exercise that we were doing yesterday. So if you remember, let's see. So all the material is in this repository. So you just go to github.com, Francisco Villaescusa, ICTP-SAIFR, right? So you go there. And we went through the first slides about, what is machine learning and these things. We went quickly through the tensors in PyTorch. And we were doing basically the problem. So let me state again what was the problem. So we have, let's say one universe, so one simulation, where, let's say omega matter is 0.3, and maybe sigma 8 is 0.8. We have another universe where omega matter is 0.7, and sigma 8 is maybe like 1.0. And at the end of the day, we have like 1,000 different universes. For every universe, our summary statistics is the star formation rate density. So basically, the density of stars that we are forming as a function of redshift. And what we have is basically a table. I think this is something that was a bit confusing yesterday. So we have, let's say, this is like the universe. And this is the star formation rate density. And let's say this is omega matter. So we have universe number one. We have some star formation rate density. And we have omega matter 0.3, the universe number two. It will have a different star formation rate density. And omega matter is 0.4. And we have all the way to, let's say, 800 universes, okay? So what we're trying to see is that, if there is a function that basically, given the star formation rate density, give us omega matter. And the idea is that, we will use 800 different universes to try to find this function with neural networks. And the idea is that, once we train this function, if we go, once we go to the universe, let's say 959, if we only have the star formation rate density, our neural network will be able to give us the value of omega matter without us telling it. Right? So that was really the exercise. Is there any question? Because I think yesterday maybe was a bit confusing. Please. It's not a large number, but it's what we could afford. If I will run 1 million simulations, I will do it. That's a super good question. I think a good number is 1,000. If you can afford more, always more, always more. But I think, with 100 is too small to really train these models. 1,000 is kind of the minimum, I would say.
It must depend on the data that you're using, how powerful it is.
Absolutely. But as a rule of thumb, I think 1,000 is a good number. Any question? Okay. So let's try to do it this. So let me go again. So please.
Suppose we want to generate 1,000 more simulations for a data set. How do we choose the values of the parameters like omega matter and
That's a very good question. So your question is like, how do you really sample the parameter space, right? So, if you have, let's say here, omega matter, and you have here sigma 8, and, how do I put points here. How do I run simulations? So there are many different ways. The most, let's say, the simplest thing that you can imagine will be to put like a regular grid. If you have n simulations, basically, if this is like a regular grid, let's say the number of simulations, how many points you put here will be, let's say, a to the square. So for instance, if you have, this is like 1,000, I think this is like, how much? 30, around 30, maybe something like that. So, you will only have like 30 different values. And, might not be super good. So there are different strategies to sample the parameter space. For instance, something that you might have here is something called Latin hypercube. Where basically the idea is that, you have, let's say if you have n simulations, let's say 5, then you split your parameter space in 5, 1, 2, 3, 4, and 5. And the same thing here, 1, 2, 3, 4, 5, right? So then you construct this thing, you make this grid. And the idea, 1, 2, 3, 4, 5. And the idea here is that you only put one simulation per row and one simulation per column. So for instance, I can put one here. So now I have one in this row. I have to put maybe another one here. And then, in the next one, I cannot put this one here because there is already one in this row. So I will have to put it here. Then here, maybe I will put it here. And then here, I only have one choice, which is this. So the difference with this is that if you have 5 simulations, you are sampling 5 different values of the parameters. If you have a regular grid, you will only have like, I don't know, like 2, right? And there are even better strategies, things like Sobol sequences, this is an entire area. So this is the strategy, if you can run simulations, you might want to sample the parameter space, depending on what you want to do, right? If you want to do a uniform sampling or a Gaussian sampling and this thing. Please, go ahead. So there are some mathematical properties about this. I'm not an expert on this, but it's a much better sampling of the parameter space than this. It's much more, I think, uniform or something like that. And Sobol sequence is even better.
So my question for you is exactly, do you think Latin hypercube is good enough?
Yeah, I think for Camos, we started with a Latin hypercube. I don't know if it's written here. We don't use this anymore. We use a Sobol sequence because it's even better. And at the end of the day, this is like one line of Python versus another line of Python. So if you can, I will recommend to use Sobol sequence or even other methods. With Latin hypercube, the problem is that, for instance, once you have decided to do this, if you have 5 simulations, that's it, right? There is not a trivial way to expand. If you now want to run 10 simulations, this thing will not work. You need to do something more sophisticated. With Sobol sequence, you in principle generate an infinite sequence. So you can.
I had the impression, maybe I'm missing, that by definition, Latin hypercube was not only that you fill each row and column, but that you then sample them in order to maximize the distance. You start doing a loop that you try to select many samples and choose those that maximize the distance.
I think that's a different thing. That's a different thing. That's not. Are you sure? Because that's a minimization problem. I don't think that's what at least a vanilla Latin hypercube is doing. Maybe it's a more sophisticated thing. But there are things like Sobol sequences that, again, I will strongly recommend to use those. Any other question? We are deviating a little bit. Please. So what I was saying is that, we have 800 simulations to train, but in total we have like 1,000. So if we go now to the simulation 959 that the network has never seen, we want to predict omega matter from this. Exactly. The input in this case will only be the star formation rate density. What do you mean is huge? Well, no, this is like, so every star formation rate density has like 100 values. Exactly, exactly. So your input vector is only 100 dimensions. Any other question? Okay. So let's do this again. So let's see. I have to select a GPU. I think for fully connected layers, you don't really need GPUs. I think you will not gain anything, but for the next thing that we're going to do with convolutional neural networks, it's going to be a big improvement. So I come back here. I'm going to upload the data. So I'm going to go to data 1. I'm going to upload the data. Okay. Yes, please. The calculation should be exactly the same, but GPUs are usually faster. All this machine learning is kind of optimized to run on GPUs. No, it's really because it's going to be faster. I mean, for instance, in this case, it doesn't really matter. But if you are training like a big model, let's say if your model trains in 1 day in a GPU, if you use CPUs, you might be waiting for 100 days. It's just that it's gonna train faster. Why? I mean, GPUs are optimized for that, right? I mean, they are able. Yeah, no, please. I mean, yeah, not sure if. Yeah, I understand the question. Yeah, but we can talk later if you want. Okay, so I'm gonna load the libraries. This is something that we did yesterday. This is just uploading the libraries. I'm gonna see if we have GPUs. So you say is CUDA available? So we have GPUs. This is our data. So remember that we have this star formation rate density. We have 1,000 of these values of this data. And for every universe, we have like 100 different values. So it's the star formation rate density at different redshift. And then we have the value of the cosmological parameters. So we have 1,000 different universes, and we have 6 parameters. Okay, so nothing like that. We were also plotting how this data look like. This is the star formation rate density for 2 different universes. It looks weird. I mean, I'm not super familiar with this kind of data, but. And then here we were just plotting, what is the value of the cosmological parameters for universe 0 and universe 1. This is where we were setting our hyperparameters. So, we were saying like the batch size is 32, the learning rate is 3 times 10 to the minus 4. Dropout, I'm going to talk a little bit later about this with the CNNs. So this is just doing nothing. Here is when we were creating the data, like training, validation, and testing. So I'm going to just run it. We were doing this. And I think this is the last part that we saw. So let me just draw the architecture, just for you to see. So what we have is a very simple network where we have basically just one fully connected layer. So basically, look at this code. In the first line, what we have is like FC1, which is basically a network that goes from input size. So input size, in our case, is going to be, can you tell me how many neurons should I draw here? How many neurons do we have in our problem? 100, exactly. Because this is basically the star formation rate density for the first redshift, for the second, for the third, the 100 values, okay? So, yes, please. Very good question. Yeah, in this particular case, yes, exactly. That's a very good question. Yeah. Okay, so we go from these neurons. We now go to, can you tell me how many neurons should I put here? As many as possible. But right now, the way that is written is basically this hidden size, which is a hyperparameter. But how many neurons you have here is what this is called like hidden size. Okay. And here we have, all the connections as we were drawing yesterday. Blah 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 blah. Everything is connected with everything. Please. Yes, this is a hyperparameter, so could be 20, could be 1,000. It's up to you. And yeah, as I was mentioning yesterday, you have to play with these things. Okay, so that's the first layer. So you see, this is like fully connected layers. Now what we have is basically an activation. So what we do is like, we just compute, let's say for this neuron, as we discussed yesterday, what this neuron is doing is basically saying, this is the sum over I of some weights multiplied by the star formation rate density for the bin I. It's just doing this linear operation. Now we have an activation function that in this case you can see that is this leaky ReLU. So leaky ReLU is basically like the ReLU, and the only difference is that, if you remember, ReLU was like this. Leaky ReLU, you have here just a little bit of a very small slope. People have shown that this improves, because you don't have these dead neurons and these things, but this is basically, an activation function. So after that, we just have our nonlinear function. This is what this thing is doing. The next thing that we have is dropout. This is something that I didn't explain yesterday. So dropout, the idea of this is that we're going to take all the neurons here, and we're going to basically put to zero some of them, like a fraction of them. So this is like the dropout. So basically, you can imagine that maybe 20% of the neurons, we're going to kill them. And can you tell me why this will be a good idea? The idea about this is related to what we were talking about the polynomials before. It's like when you randomly put to zero some of these neurons, you are really forcing to learn several models. So you can imagine that, maybe in the first case, you kill the first 3 neurons. So, these other neurons are, let's say, forced to learn the function. But the next epoch where you train, maybe you are killing these 3 neurons in the bottom. So now this is kind of try to learn another model. So at the end of the day, by doing this, you are not just learning one model, you are learning like a family of models. Exactly. I'm pretty sure people have tried to even play with that, but yeah. So that's the idea, because if you don't do these things, it's super easy for the network to, let's say, overfit, right? If you have like thousands of neurons here, you might be able to learn, very quickly the real data. And again, now with all these other double descent, maybe this is not a problem, but I think people still use these kind of tricks. You are just learning a family of functions instead of one. So, for instance, if we have another layer here, and you kill this neuron, it means that there is no information going from this neuron to this one. In practice, how this is done? That's a good question. So, how this is done in practice? So I don't know if you really you put maybe these weights to zero. I think maybe this is really the way, but I have to double check. But it just means that there is not really information going from this to the other one. Please. But if you think about this, for instance, if you put the weight here to 0, it means that for the particular neuron that it was here, you are not really passing any information, right? You are really passing 0. So it doesn't really matter what is the value, for instance, of the star formation rate, it's always going to be 0. So that's really the meaning that it doesn't really matter, right? You are killing that information. Yes. Yes. So it depends on the activation function, but dropout in general, you really set this to 0. I mean, you really kill the neuron. So it doesn't matter on the activation function principle. Any more questions? Okay, so the last thing is that, we have another, this is the final thing, we have another fully connected layer, and this fully connected layer is written here, sorry. So it goes from this hidden size into our output size. So can you tell me how many neurons should I draw here? 6, exactly, which is the value of our cosmological parameters and the astrophysical parameters. So that's really the network that we have here, super, really simple, kind of the most basic thing that you can do. Please. Yes, so it's basically written here. So this is like linear, basically stand for fully connected. It's like you are using this. Every model like this is really just doing this. It's doing a linear combination. And then you need to define your activation function. And that's it. Okay. More questions? We talk about, yes. So, I mean, the network is going to see all this data, the 800 simulations. When you see all the data, it's called one epoch. So we're going to see that we're going to train this, I think, for 100 epochs. So we're going to see all the data 100 times.
I was thinking that the first row of neurons being would refer to the entirety of the data.
No. Yeah, no, that's very important. So you only pass the data from one simulation. Because, I mean, you could in principle pass data from 800 simulations. But then when you test the model, you will need 800 simulations, right? You cannot change the size of the model one is trained. Other questions? Please. Yes, it's another hyperparameter that you need to define. So in our case, let's see how much I put this. So the dropout is set to 0.2, so 20% of the neurons. But, it's a hyperparameter. I have trained models when I put maybe 90% because, maybe you are overfitting very fast. So, yeah. Other questions? Please. One epoch is all the data that you have to train. So we will see the data 100 times, all the data. Because, when you see the data only once, maybe, and remember, we are doing this. So the whole data is the data from 800 universes. And we will be seeing. Yes. Yeah, I mean, at the end of the day, will be 800 times 100, right? 80,000, I think. 80,000, yeah. Not in one go. Let's look at the code. It's going to be very clear. Any other question? Yes, please. Mm-hmm. You say what they are? What they mean? Yes, okay. So I haven't talked about it. It's not very important. So when we run the hydrodynamical simulations, we use subgrid physics. I think this is what Roman maybe told you a little bit. So, we cannot really, in this simulation, really simulate a supernova, right? A supernova happens on scales that are much smaller than the cosmological scales that we have. So right now, it's impossible for us to cover all this dynamical range. So that's why, we have kind of phenomenological models in the way that we explode a supernova in a computer. And this model has some free parameters, how much energy you release. So these parameters basically parameterize that, how much energy you release, how fast this energy propagates, these kind of things. More questions? Yes, please. What do you mean is noisy? Yes, I'm not sure if I understand, but the dropout, what it's doing is that you have a set of neurons, right? And it's going to take a random, let's say a random 20% of them, and it's going to put them to 0. That's really what the dropout is doing. Just basically killing 20% of them, let's say. Okay, so let's run it. So you have seen now the architecture, right? So you see, this is a very small network. We only have like 10,000, 11,000 parameters. Remember that these days, of course, like the big large language models, we don't even know how many, but they have like trillions of parameters, probably more. So, okay, so the next thing that we need to do is to basically define, what is going to be our loss function. And our loss function here is basically the mean square error. And if you remember, so, we have omega matter, we have sigma 8, and we have these supernova parameters. So our loss function is going to be this minus this. So this is like the neural network. This is like the true value square plus, and this is the same thing, sigma 8 true plus, and the same thing here, right? So this is our loss function. This is what we are really trying to minimize. So we want to be the prediction of the network, omega matter, sigma 8, and these astrophysical parameters to be as close as possible to the true value. So, and then we define the optimizer. This is the way that you do this gradient descent. And I will not go into details, but Adam is a very good model, optimizer. Okay, so now we are going to train the network. So what we do is basically the same thing. We do a loop over the number of epochs. And if you remember, I think here we have like 300 epochs. Sorry, not 100, 300. So the first thing that we do is to make a loop over the number of epochs. The second thing that we do is basically we do a loop over the data itself. So in our case, we have 800 star formation rate density. We are going to go through these 800 points, but we're going to go through this batch by batch. And if you remember, every batch, it was of size 32. So we will take, let's say, maybe the first 32 star formation rate density, then we go to the next 32, all the way to 800. Please. Mm-hmm. Yes, so this is Yeah, very good question. So this is what I was mentioning yesterday, if you remember. So this drunk person going from New York to Los Angeles, you can in principle take the 800 simulations, right? And just, let's say, have a batch size of 800. So the derivatives, when you compute the derivatives with respect to the loss, are going to be they are not going to be very noisy. They are going to be kind of perfect. If you fall in a minimum, then you are lost, right? And there is no way that you will fall, because the minima give you a gradient of 0, you are done. If you use a batch size of 1, you go one by one, it's going to take forever, and the derivatives are going to be very noisy. So that's why you want to be something in between. And that's why 32 is a good number, so you estimate the derivatives are noisy, and that's good, because you don't fall in a minima, but still, like the drunk person, you might still be able to find your way. Yes. Yes, exactly. To train, if you can see here, this is really where we take the data and we send to the GPUs, and the GPUs are the ones who are doing all these calculations, Like a node. You don't partition the data. Not sure if I understand you. The reason to use GPUs is just because it's faster. Really, there is no other reason. Belén, you want to say? Yeah, I mean, if you... Yeah. Yeah, I mean, my understanding is that this thing is done things in parallel inside this, so that's why they are at the end of the day much faster. Mm-hmm. Okay. So this is like the main loop. So everything that we're doing here is saying, okay, so for this batch, I know the value of the cosmological parameters and the astrophysical parameters. I know the star formation rate density. I'm going to pass this to my model. So remember, our model is like these fully connected layers. I'm going to compute the loss function. And this is where all the magic happens, right? This is the way that you compute the partial derivatives of the loss function with respect to the parameters, and the way that you optimize, the way that you update the value of the parameters, right? So these 3 lines. And once I have done an epoch, so in this loop, once I've done an epoch, what I'm going to do is I'm going to pass my data into also the validation set, and I'm going to compute the validation loss. Please. If I'm going to say again? Yes. So let me. So, in our model, we have all these weights that we were talking, right? So this is, for every neuron, we have all these weights. And these are really what we want to optimize, to basically learn this function. Okay? So, when you start with a network, you just have like some random values. So, maybe W0 is 0.3, W1 is 0.7, things. So that's why, with random values, you will not do very well. So what we want to do is basically, is like the value of wi, we want to change to be wi minus the learning rate, and then the partial derivative of the loss with respect to wi. So if you remember, it's like if we have this kind of, let's say, maybe loss function, and we are sitting here, the derivative is going to be like this. So what we want to do is to move in this direction. So that's why we have this minus sign here. And to compute the slope, we are computing the partial derivative of the loss function with respect to the weight. And then, given this prefactor, the learning rate, we will be moving this point to this point. And from this, we go to here, to here, to here, and eventually, we might be able to come here to the minimum. That's it. Yep, exactly. I think that some people say that it's like going down a mountain, right? You just compute the slope, you always go down, and eventually you will go to the valley. It's really that. Okay, so that's really it. So let's execute this. So now we are training the model. You can see how fast it is. So in the first column we have the number of epoch. Epoch 0, 1, 2, 3. This is the training loss, and this is the validation loss. So you can see, I think, how the loss is going down. And every time the loss is better than another model is basically saving the model. So you see the loss is going down, 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 down a little bit. And at some point, as you can already see, it's kind of plateau, right? So this is a toy example. We trained this in 11 seconds. But we have now our model trained. So now what we can do is basically, this is just to plot the loss function. So you see, this is how things look like. I think maybe the blue is the training loss, and the orange is the validation loss. So you can see initially it's go down very fast, right? It's learning very fast, but at some point it's going to kind of plateau. It's like, there is maybe nothing else to learn. This is really what it is. And this is the typical behavior. If the orange line starts going up, if the validation loss start going up, what is this behavior? What is happening? You're overfitting, exactly. So that's a time where you might not want to take those models. And if you leave it running for a long, long time, as we explained, it might go down again. OK, so let's test the model. So for testing the model, really exactly the same thing. You read the data. Now you pass into the data. And basically, yes. So let's run this. And now let's plot it, right? So this is like the final thing. So this is, I believe, this is for omega matter. So every point there represent, represent a value of the star formation rate density from a simulation that we have never seen. We are passing it into the neural network, and the neural network is now predicting the value of omega matter. And there is this line there. So this line is the diagonal line. So if you will be on top of this, it will be like perfect, right? It will be like a perfect prediction. You will predict omega matter with a perfect prediction. You can see that there is some scatter, but it clearly has learned something. There is a correlation there, right? It's very clear. And again, you have seen how simple it is. It's like, I don't know how useful this thing is, but we are going now from something like the star formation rate density directly to the value of the cosmological parameters, right? And we have done this in maybe 1 hour. So you can explore data, because I really don't know how to even write a model to go from the star formation rate density. You can ask David who likes this thing, but I will not be able to do it. But in principle, for very complex observables, You can just see if this works.
So if there were no correlations, suppose that star information has nothing to do with one another.
Yep.
They just have starting point.
Not really, Rogerio. I think we can even test. So let's see. So this is for omega matter. So let's see if we do this. I think 1 will be for sigma 8. So let's see if this works for sigma 8. OK. So still there is a correlation. So let's see for these astrophysical parameters. So for these astrophysical parameters, OK, you see there is still able to predict this, I don't know, supernova feedback, whatever. But let's try another astrophysical parameter. OK, so this is exactly. So this is, I think, AGN feedback. So we know that in this simulation, because they are so small, AGN feedback doesn't really change too many things. So basically what is happening is that there is really no impact of the AGN feedback on the star formation rate density. So what the neural network is basically predicting is basically the mean of the distribution. The network knows that omega, this parameter goes from this maximum to the minimum because it has seen it in the initial table. But it doesn't know which value should be there. So the best thing that it can do is just to predict the mean. It can be shown, I think, mathematically that this is really what minimizes the loss function, and it means that you are just not learning anything. You are just predicting the mean of the distribution. If we will be doing inference, it will be shown that you will predict the mean with a very large error bar. So that's why you are really covering all possible values.
If you have some prior knowledge of the parameters, it would go all in the ranges of the...
Exactly, exactly, in the way that you train. So this is already learning the priors.
Yeah, the priors are there.
Exactly, exactly. And it can be shown mathematically. This is maybe something that not many people know. We're using the mean square error, which is basically this. It can be shown mathematically. It's very easy. That when you do this, you are really computing the mean of the posterior. It's like if, we know that there is a distribution, there is a posterior distribution, and what you are really doing is computing the mean of the posterior. And that's why precisely here you just predict the mean value. Yep. So what it's doing, yeah, let's go step by step. So the loss function is just defined here, and just saying that this is like the mean square error. And it's really what is written there. So when we do the training loop, we are here really optimizing the weights. This is the way that we optimize the weights. But in the validation loss here, we are just basically computing the validation loss, and we are saving the model. These are the lines where we say that if the validation loss is smaller than the minimum value, then we are going to save the weights of that model.
Oh, so you're just saving for, just in case of the loss of the validation
Mm-hmm.
is lesser than the minimum.
Yes, so let me maybe make a drawing quickly. So let's say that this is like epoch, okay, and this is your loss. So let's say that your training loss is, I don't know, something like that, okay? And your validation loss is, I don't know, something like that, okay? So what we're saying is that, let me see. So for every epoch, you compute, for instance, here, you will save the weights because these are smaller than anything before. So you come here and you say, okay, I'm going to save the weight, but now I'm coming here, even if let's say the training loss will be lower, I'm not going to save the weights because the validation loss is higher than this value. Yeah, exactly. The validation loss is the most important thing.
By minimizing the training loss, and at some point you're going to be minimizing the validation loss.
Yes.
When you surpass the overfitting time, it's going to go up.
Yes, if you are overfitting, in principle, the validation loss will go up. So remember, we do this for the training set, right? the way that we update the weights is always for the training set. But to save the model, we only look at the validation loss. Yes, so the hyperparameters here are fixed. You know, we are not really changing them. You can iterate later over this, but we are not doing this here. Exactly, exactly. Okay.
How can you be sure that they're not setting local minimum?
How can you know? You don't know. In fact, I think in machine learning, we know that usually we don't reach the global minima. We don't even know when you have trillions of parameters. But what people say is that, you know, a good local minima is good. Yeah, usually you don't really find the global minima.
So the spread and the correlation gives you an idea of the uncertainty?
Yes, I mean, here again, we are doing regression. We are not doing inference. There are ways to do inference where you will get like an error bar. You can get covariances, everything. But yeah, here I think you can probably see that, you know, the scatter will give you a little bit an idea of, let's say, maybe the error of the scatter. Yeah. Other questions? Okay. Great. So that was all for fully connected layers. I think, you know, my plan now is tell you about CNNs. So let me see. I don't know why this you cannot go back like a normal person. You have to do all these things, but I don't know. So okay. So let's go to convolutional neural networks now. And the idea that we're going to be discussing is like, what about if, you know, our data is more complex? That, you know, maybe just a simple array, a simple vector, like what we're working here. You know, what about if we have images? You know, how can we do this? So let's say that, you know, you have, you know, an image. I don't know. Let's say that you have here maybe the cosmic web, something like that. You know, some kind of filament, whatever. So, you know, do you think that we can process this kind of data using like fully connected layers? Any thoughts about this? Yes. So let's say that, you know, your data is an image, and my question is like, can you use fully connected layers to, let's say, train on this kind of data? Yeah, let's say that also here, you know, is a problem where we want to infer omega matter from this image, something like that. One number, yeah. Yeah, but that's fine, you know, because even here, this star formation rate density, these still have some correlations. If you will remember, these curves are always kind of like this, so there are correlations here. And the fully connected layers take into account all that. Okay, so the answer is usually not. I mean, you can, in principle, you know, you can say, okay, so this is like my first pixel, this is the second pixel, this is the third pixel, the fourth pixel. You can put this as every single neuron. In principle, you can do this. And this will be fine, you know, I mean, there is really no problem. So what is the actual problem about this? So the actual problem about this is that, you know, usually, I mean, images are relatively large, right? Let's say that at least you have maybe 256 by 256 pixels. So this is already like, I don't know, but a few thousands values. So let's say that your input neurons will have already like, you know, maybe 60,000 neurons. And, you know, if you want to put here something like 1,000, you will already have like millions of weights, right? So already training on something like that, it will be like super, super expensive. You will have like millions of parameters. So training something like that will be super complicated. Okay, so that's the idea basically of what, you know, people invented kind of convolutional neural networks. So the idea here is that, you know, you have your image, and you will have, as we will see later, basically like a filter, right? And this is going to be like a single filter that you are going to pass through the entire image. So let me illustrate this. So imagine that, that your data, let me see if I can. So imagine that your data is something like this. This is your image, just for simplicity. And imagine that the only thing that you are doing is basically convolving your image with this filter. So, in practice, what this means, I have this illustration that I steal from someone in internet. It's basically you put the filter on top of the image, and then you do, for instance, if you put here in this corner, you do 1 times 1, 1 plus 0, 1 times 1, and basically you sum everything. So you go from this image into this, let's say, convolve feature. And why is this useful? So here you can see, for instance, what this usually produces. So imagine that your image will be this super weird thing. I don't know what this thing is, but and imagine that your filter is just 1, right? So you are not really doing anything. So if you take the image and you multiply by this filter, you get the image. I mean, you are not really doing anything. That's, let's say, the identity. But now imagine that your filter is something like that. Then your image will look like this. I don't know how well you can see this, but these kind of things are designed to do this edge detection. Like, for instance, here, you can clearly see that it's able to emphasize the edges of the image. Or, there are filters that are designed to sharpen the image. People working in images processing, they know these things very well, right? They have been doing this for decades. Or, you can blur the image with, a normalized box or with a Gaussian approximation. So, depending on your filter, you might be able to extract some features about the image. Please. Yes. But this is, it's kind of basically the same idea, but in real space, yeah. So, I mean, imagine that, I don't know, there is cosmological information in, I don't know, the filaments. Let's say we're looking at the cosmic web. You might want to design a filter to extract that information, Instead of using maybe by hand, some handcrafted summary statistics, super complicated, you might want to say, okay, so I have some filter that I don't know what it is, but I can use a neural network to find the optimal weights of this filter. So this thing can really extract the relevant image, the relevant parts of the image. So this is a little bit how CNNs works. A CNN layer is basically a set of filters where the numbers here are your free parameters. This is what the neural network is going to optimize. This is what the neural network is going to learn to basically extract, let's say, most of the information that you care in your image. So maybe to associate this with something that maybe you have heard, this is related to this thing that we call field-level inference. We have been talking about the power spectrum. I think maybe David and others have mentioned that the power spectrum on small scales does not capture all the information. I think Roman emphasized this a lot. And still, we don't know how to extract all the information. But you can, in principle, use these kind of techniques to basically extract all the information, all the relevant information. You can just learn that. So this is kind of a simplified version of doing this field-level inference, where you might be able to just extract all the information.
So is it like a compression technique?
Yes. So in this case, it's kind of a compression technique. Well, I mean, we can discuss this later. This is a huge debate. But in principle, I'm not sure how to answer that question. I'm not sure. People have tried with different methods that in principle, they don't lose any information and they get, I think, very similar values. But
because the problem is to use the original map is too big, it's too large. So you have to do some compression.
Exactly. Well, but yeah. So that's exactly true. So basically, yeah, you have this filter, and this filter is something that you will use across the image. So in that sense, but I was maybe referring about compression for another thing that is going to be clear later.
So basically,
Very good question. Very good question. So the way, let's say, what we're going to be doing today is going to be something like that. So we will have an image. We're going to train this on also images from camels, so state-of-the-art hydrodynamical simulations, and we're going to pass through a set of filters. And the images are going to be smaller and smaller with time. You will see later. So if you start with, let's say, 256 by 256, maybe after the first pass into the CNN, you will get maybe like 128 times 128. And maybe the next pass is going to be 64 by 64. And maybe at some point you will get 8 by 8. And you will say, OK, this is already small enough, so I can just flatten this thing and just train a fully connected layer, which is exactly the last step. OK, so this is important. It's clear. We're going to pass, this is basically, you can imagine that like a set of filters. We're going to reduce the dimensionality. Then we are going to go to another filters, reduce the dimensionality even more and even more. And this is a little bit a way to capture like all this hierarchy in scales. Maybe in the first pass, you are just learning, maybe the edges, maybe something about the morphology of the image. But now when you apply a filter on top of this, you are learning these kind of higher order things. And it's kind of a way to extract information from all the scales.
I never had this perspective on CNNs. Because, yeah, you know that CNNs are used to extract features, specific features for a specific image. But if you could simply flatten the original image, basically you would get the same result, but with a lot more of processing.
Exactly.
Maybe do that just to reduce the size of the image.
Yes, yes. I mean, they have a lot of very nice properties, inductive biases. As I was mentioning the other day, people don't use CNNs anymore. These days, people use transformers, that it can be shown that they work even better. And I don't think we will have time to go into vision transformer and these things. But vision transformer, what they does is basically, they take an image, they flatten out, and then they pass into a transformer, roughly. So it's kind of maybe going a little bit back to the fully connected model. OK, so the thing about this is that every CNN layer doesn't have to have a single filter. How many filters you have, this is also a hyperparameter. You can have a filter or you can have 10 filters or 20 filters. This is up to you, right? In principle, the more filters that you have, the more rich the information that you will be able to extract. Because maybe one filter is going to sharpen the image, the other is going to blur, the other is going to do this edge detection. So, but this is a hyperparameter, how many filters you have. OK, so another important thing for this is the padding. It's like, sometimes you have an image, and sometimes you basically need to put, let's say, you need to extend the image a little bit more for technical reasons. So, you can just extend, let's say, your image. You can put zeros, or maybe you can put other numbers. You can, sometimes in Cosmology we have, let's say, simulations, and maybe this is like an image, and this is periodic. So maybe instead of having 0 here, you might want to put 4, because this is, is periodic. It's like a simulation. And the way that it works here is exactly the same thing, right? So you have your filter, and your filter will basically go through the image, and you're basically computing the numbers there. OK, so another concept is the strides. You have seen that we have this kernel that is basically moving across the image. But how much do you move? You can start maybe in this first square, and you can say, OK, so now I'm going to move to the second one. But you don't have to do this. Maybe you can go to 2 values after that, or 3 or 4. This is what we call the strides. So it's basically just how much you want to move this filter. And something that is important, again, if you ever use this thing, is like, given the size of an image, you want to predict what will be the size of the image that you will produce after convolving with your kernel. So for that, you have to use this formula where this is the size of your image, this is the padding that you do, this is the size of your kernel, and this is the strides. If you are designing CNNs and this thing, you need to take this thing into account. Yeah, I mean, sometimes the problem about this is that sometimes you, I don't know, for instance, imagine that you have an image that is 5 by 5, but you are moving 2, then you will not be able to get to the 5, right? Because it's 2 and 4, but you don't have the 5. So in order to avoid all this problem, yeah, you will need to introduce padding and these kind of things. So that's really, yeah. Okay, so just to mention that, there are many other hyperparameters. These are really the basic ones, but there are other things. I'm not going to go into details. Another thing that is important for CNN is about the pooling, right? As I told you, what we want is to have an image, and we want to reduce the dimensionality. So how do you reduce the dimensionality? So sometimes what we do is to use these pooling layers. So let's say that this is your image, and now you have a pooling layer that is 2 by 2, okay? So for instance, if you use this max pooling, what you are doing is saying, okay, so from all these pixels, I'm just going to take like the maximum value, which is 20. And this is going to be my pixel. I'm just removing all the other ones. So for instance, here I will be 112. So this is a way to just reduce the dimensionality of your image. There are other possibilities like average pooling where you have, let's say, this kernel, and you just compute like the mean value inside it. And I think I have an animation here that does just show you, how this is done. And I think this is all for CNNs. Yep. Any question until here? Yep. Yes, I was talking with Raul, I think, before about this. So I think the best strategy for doing this is to do both, right? If you already know some features that are good, use them, right? I mean, the network might learn this thing, but if you already know them, use them, and then you can combine this with a network that might learn something beyond that. So for instance, the power spectrum, right? If we have an image, this thing can learn to compute the power spectrum. Instead of predicting omega matter, you can have the task to predict the power spectrum. It can do this. But if you already know how to do this, just use it. Otherwise, this will take a very long time just to learn to compute the power spectrum. So these days, people use this thing that is called hybrid networks, where you might want to use the power spectrum of the image and then use a CNN to extract information beyond the power spectrum. Because then, you don't need to learn something that you already know. And, I mean, I did this exercise a few years ago. It takes a very long time to learn how to compute the power spectrum. And it's something that, you can just do in 2 lines. Okay, any question more about CNNs? Please. Talk louder. To find cluster of galaxies. I'm not sure for that particular thing, but I mean, in astronomy, there is I'm pretty sure hundreds of papers using CNNs for all kind of things. Yeah, I think, again, I have to be careful with what I say, but yeah, I think in industry, people don't use CNNs anymore, I think. It has been shown that transformers are more powerful, even for images and these things. So these days, people are moving. But the problem with transformers is that you need a gigantic amount of data, right? So if you don't have a lot of data, still CNNs usually will probably perform better. So depending on what you do, I think you have a question also. Mm-hmm. Okay, so let me see if I understand the question. There was another. You want to answer him or? Okay, let me. Sorry. I mean, as you say, yeah, this thing is basically designed to find patterns, really. And for instance, these days with CNNs, these machines achieve superhuman, for instance, capabilities. If you want to distinguish between cats and pets and all these things, it has been shown that this thing is already better than us. And at the end of the day, what they are doing is really finding these features, that, we are doing maybe, I don't know if this is how our brain works, but we also find patterns and features, right? This is the way that I think we distinguish things. So at the end of the day, and I think your second question was like, you will lose some information. So yeah, potentially yes, absolutely. But at the end of the day, if I think Cosmology will expect that there might be some summary statistics that might be able to fully characterize the image, like the power spectrum for a Gaussian field. So in principle, this will be kind of the equivalent. This will be a kind of summary statistics that is able to extract the statistical properties of the field. Tomorrow, not today. Yes. Well, what we're going to talk tomorrow is going to be used for unsupervised learning, for large language models. It's going to be completely unsupervised. But that class is going to be a little bit theoretical. That's going to be, we're not going to train anything. Belén. Yes. I mean, CNNs works very well. And again, I don't want to say anything wrong, but still I think for things like self-driving cars, I think they are still using CNNs because they are much faster than transformers. So they are still very good, but people in machine learning, they care a lot about so they have been shown, I think, that transformers are better. I think really the key here, and something that I haven't mentioned, is about these inductive biases, right? So for instance, CNNs still they have some inductive biases. There are some assumptions that we're making. Like for instance, here is like translational invariant, and there are other properties. Transformers have very few inductive biases. So that's why they are in principle much more powerful. So if you, let me explain this because this is an important concept, what this inductive biases. So let's say that you are trying to feed, I don't know, some data that is like this. And you might say, okay, so I want to use only, let's say, functions that are quadratic, things that are like, I don't know, A plus BX plus C squared, I'm only going to use this kind of term, right? So, I mean, you might do better, right? And in this case, you only have to fit for A, B, and C. So it's going to be very fast. But as we were discussing later, maybe you want to add more things here. So in this case, your inductive biases will be lower, let's say, because you are making less assumptions. You will have more parameters, so you will have to train this longer. It's going to be more costly. But in principle, this model will perform better than this, in principle. So that's exactly the same thing with transformers. Transformers, maybe it's what you were saying is, I'm not sure if it's the number of parameters, but they have less inductive biases. They are making less assumption about your data, let's say. And that's why they are able, with a gigantic amount of data, to perform better than CNNs. There was a let me see if I understand your question. Are you saying that if your data is simpler, it's maybe just a vector? If it's a vector, I will just recommend using fully connected layers. Fully connected layers, they have very few inductive biases. So that's why, this thing in principle is the most powerful thing. But it's hard to train, and, if you have a lot of parameters like an image, then yeah. Or imagine that you have the whole internet to learn on that. You cannot use these methods. Yeah. Yes, I'm not sure if I fully understand what you're saying. Maybe we can talk later because I'm not sure if I understand. Yeah, just to don't say anything that is wrong. Okay, any other question? Yeah, please. Oh, very good question. Your question is, what is the advantage of this over this? Yes, so that's a very good question. So with mass pooling, let's think about this. So what are we doing? Are we just basically taking the maximum value here? So what we're doing is basically throwing away information. This value of 12, 8, 12, this is something that we are throwing completely away. Because, if this number, instead of being 12, will be 13, the result will be exactly the same. If this number, instead of being 8, will be 10, it will be exactly the same thing. So in this case, you are really throwing away all this information. With average pooling, you are not doing that. You are still, if you change any of these values, the average pooling will still. So in practice, I believe that the max pooling still works better. This is a little bit the black magic of machine learning. So I believe from most of the things that I do, I still use like mass pooling. Or sometimes what people do is to use like the two different pooling. You don't have to pool in one way. You can pool in two ways, and then you can combine the result. But I think in practice, even if this is a little bit less intuitive, this works better because it's not only about losing information, but also about the gradients, that you don't, yeah. There was another question, I believe. Yes. No, I think it was you, no?
So it was basically the same question as her, but what she was saying is that basically when you compare max pooling to the average pooling, I try to think about like, imagine that
basically bringing down the luminosity of the object to the noise level. So if you just take the maximum pooling, in that case, you would like literally take the maximum value of the pixels.
Mhm.
You would like raise the area of the image in that sense when it comes to luminosity comparing to the noise. But my question was not that. I would just ask if the when you take the pooling into account,
Mhm.
is it like extracting something or just reducing the size?
Well, yeah, that's a good question. In principle, you are really losing information, right? Because doing any of these operations, you are losing information. So it's really designed to reduce the dimensionality. Because if you have an image and you always keep the size of the image, this is not going to be very useful, right? At some point, you want to reduce the image so you can, Yes, probably. Again, I don't want. Yeah, the way that I have learned this, maybe other people will say that no, but yeah, I think for us it's really to just reduce the dimensionality. Okay, so I think there are only like 10 minutes, so maybe I will show you the notebook tomorrow. It shouldn't really take like too much time, and then we will go with the transformer model. So, also in preparation for Friday, for the different groups, if you have some data, we can try to write a paper about that. So, I don't know, if you are working on a paper and you have some data, the data shouldn't be like very large. So, maybe 1 gigabyte, maybe 10 gigabytes, something like that. And we can give a try. Otherwise, I can share some data with you, but it will be very nice, if you have some data and we might want to write a paper with this. The data doesn't even have to be in cosmology, it can be like other things, but I believe. Okay, so tomorrow, if you can find me, the representatives, so remember, talk to Rogerio, Gonzalo, Belen, and I think Natalia, I forgot, but all these people that we say. So talk to them, just choose a representative, and tomorrow if you have, let's try to install the code, should be like 5 minutes, and then we prepare. I think this is the first time that no one has ever done anything like that. It's like this crazy guy told us to write a paper. So, yeah, so I think maybe it's a good time to stop here. So, thank you. There was a lot of questions, yeah, so it's already maybe they are tired.
I have a quick question. Since we're talking about data compression, how about PCA? Is that one technique that is used in this field?
Yeah, definitely. But this is, I would say, more classical. Machine learning is an example of this. With deep learning, you try to go beyond that, like non-linear PCA. That's a way to see this, yeah.
You have a question? No.
What about doing pooling, but with some random process, like you add, I don't know, like you don't just stick to one value, but you do something to it, like is that?
Say again, Gonzalo.
I don't know. You do some random thing to the data. Like,
yeah.
Is that something that has some value or not? For pooling, for example. I don't know.
For pooling, you lose information, and your question is like whether.
No, you do some randomness to the data, for example. Is that just asking?
Whether this will influence the result, or
will that be something to do or not? You don't want to perhaps lose. I mean, it's just a stupid question.
Yeah, no, I think. Yeah. It depends. Yeah, I guess you need to train the model and see, whether this really have an impact and maybe change. If you are really losing much information from your layer, maybe you want to change. Yeah, I think it's hard to say any quantitative statement about this.
Going once. going twice. So remember tonight, 7:13, the restaurant in Alameda Santos for the social dinner. But one last question first.
I'm just gonna ask, like, maybe you explain, but I don't understand what do you mean by writing paper on Friday? A paper, what?
You will see tomorrow. You will see. So in principle, the way that this works is we will have some data, right? So we will just explain the data. And what this thing is going to do, this is with agents. So, on Thursday, we will write some of these agents, for instance, to generate ideas. So the first thing that it's going to do is, like, given the data, it's going to generate an idea for a project, right? It's like, I don't know, I think we should do this and that. So just an idea. Once it generates the idea, it's going to make a research plan. So you say, okay, so, I don't know, let's say that we are using data from camels, and it's going to compute, I don't know, I want to infer omega matter through wavelets, scattering transform, something like that. So then once it generates the idea, it's going to say, okay, so I need to do a research plan. So first, it's like, okay, so I need to read the data. I need to normalize the data. I need to compute the coefficients for the wavelet scattering transform. And then I need to train a neural network to go from the coefficients to omega matter. And then I need to basically write a section, something like that. So when it writes a research plan, it's going to go point by point. It's going to write code. It's going to execute code. It's going to make plots. And at the end of the day, it's going to write an entire paper. So you might be amazed about this, believe me. So yeah, in principle, it's going to be like a full paper. I don't guarantee that it's going to be a good one,
So the format of the data can be anything, like
anything,
files?
Anything. You cannot have an idea of how many things I've been doing with biologists and neuroscientists these days. They send me this super weird data. In biology, for instance, the data is letters. I mean, again, I'm mid-recording, so I don't want to say, this crazy guy. But they use like genes. I think they use exactly. That's the data that they send me, and still it was able to work very well. Can be graphs, can be unstructured data, anything. So that's going to be the.
Region. I don't know how to say it. Like, it's maybe it's like plotting some plots with like correlation is not causation.
Yes.
He's also producing some papers by like from random data. It's like producing some papers with some agent, something like this you're talking about probably. Maybe if you don't see it, maybe you don't.
Yeah, I'm not sure if we're talking, but you mean that these are like crazy papers, like bad papers?
No, just like just creating an AI agent create some random paper just to show some data.
Yeah, I think it's going to be the very same idea.
Yeah, just like sunspots explaining, mortality rate or something that is not correlated, and you probably get this thing that you showed, right?
Yeah, I mean, you will see it's really, really good. So tomorrow, I mean, in the colloquium, I will also try to write a few papers, and I know it sounds crazy, but this is really, maybe this is the first time that you heard about this, right? So it's really like crazy, but people in machine learning already has been doing this for maybe 1 year, and this is coming. So, it's, yeah.
Looking forward. Thank Paco.
Thank you.